Okay, this is our first example in Unit 4 on probability. In this example, we're going to be calculating the odds of drawing a queen from the deck twice in a row. So the first question we have to answer before we even begin the problem is about the draws that we're making. So there are two sorts of ways to draw a card from a deck of cards. On the one hand, we can draw the way we normally do in games like Uno, or games like Go Fish, for example. And that is, we can draw from the deck and not replace the card back into the deck. So we draw and we keep it, right? So in those sorts of games, you keep it in your hand. But the idea is it doesn't go back in the deck. It stays with you. So we call those sorts of draws a dependent draw. Another way of thinking about this is dependent events, because dependence is not just about deck drawing, it's about events in general. But when it comes to events like decks, right, like drawing from a deck, you can think about it as without replacement, right? So a dependent event is one where you're not replacing the card back into the deck. So it is a draw without replacement. On the other hand, we can do the exact opposite. We can replace the deck, we can replace the card back into the deck. And that is an independent event, right? So drawing with a replacement, where you put the card back into the deck after you draw it, that is an independent event. And so what do these two terms mean? Well, an independent event means that the first event doesn't affect the second. So two events are independent just in case the first one doesn't affect the second one. On the other hand, two events are dependent just in case the first one precisely does affect the second one. So another way of putting this is that two events are dependent just in case the outcome of the first event affects the outcome of the second. All right. So now let's look at what we mean here by twice in a row. So another way of putting twice in a row is really this. What you're really asking is that you draw a queen and you draw a queen. So in other words, there are two events, event 1 and event 2, and you have successes in both of them. And what qualifies as a success is drawing a queen. So this is a conjunction. This is why we call these sorts of probabilities conjunctive probabilities. Right? They're conjunctive probabilities precisely because they demand two successes or two results back to back, right? In two back-to-back events. Okay, so the way that we do conjunctive probabilities is we represent them with multiplication. And so then the idea is you're multiplying the probability, I'm going to represent that with prob, of event 1, so E is event, multiplied times the probability of event 2. And so our formula as applied to this question is really just you multiply the probability of drawing a queen times the probability of drawing a queen the second time. Right? So you multiply the probability of drawing a queen in the first event times the probability of drawing a queen in the second event. Well, so how do we know what the probability of drawing a queen is? Well, remember our probability formula from the very beginning that we learned was probability is just the outcome you want, so your successful outcome, over your total number of possibilities, over all your possibilities, right? And so if we think about the very first draw, we want to draw a queen on the very first draw. How many ways are there to draw a queen? So how many ways are there to have a successful outcome? Well, it looks like there are 4 ways, right? Because there are 4 queens in a deck. But how many possibilities are there? How many different cards can you draw? Well, that's a much bigger number. That number is 52, right? So that number is enormous. There are lots and lots of different cards you can draw. And so now we ask ourselves about event 2. And event 2 is a little bit harder, right? So event 2 is the one that could potentially be affected, right, by event 1. But we are talking about the independent form of this calculation right now. So we're talking about drawing a queen twice in a row where you have replacement, where the two events are independent. And so even if I get my queen in this first event, even if event 1 with its low probability turns out in my favor and I get a queen, I still have to put it back in the deck. And so the deck is going to look exactly the same for my second draw as it did for my first draw. So that means, once again, there are going to be 4 possibilities, because there are 4 possible queens. So there are 4 possible successful outcomes. Divided by 52 is the total number of possible outcomes. And so if we go to multiply this, and let's multiply it by hand just for posterity's sake, we know that 4 divides into 52 13 times, so that gives us 1 there and 13 here, and 1 here and 13 here. And 13 times 13 you can certainly do on your calculator. That seems perfectly reasonable, but it is 169. And so that means your likelihood is 1 in 169. That's the probability that you're going to get 2 queens in a row if you pull twice. So that's really, really low. But now let's look at the dependent event version. So where you don't replace the card that you draw. So again, this is going to be a multiplication problem because we have conjunction. You're still asking about drawing a queen and drawing a queen. And the probability of the first event is going to be the same because the deck looks the same at the beginning. Right at the beginning, I still have 52 cards and I still have 4 queens. But the problem is now figuring out what this probability should be. And so let's think about that for a minute. If I want the probability that I draw a queen and a queen, then I want to assume success for my first event. I want to assume success for my first draw. Because if I didn't draw a queen the first time, then whether or not I draw a queen the second time doesn't matter. It's still a loss. It's not a success. Right? So it only counts as a success if I draw a queen the first time and then something special happens the second time. Right? But without drawing that queen the first time, there's no way I can get a success. And so that means that I need to assume, for the sake of the second event, that I've drawn a queen. If I assume for the sake of the second event that I've drawn a queen, then that means I've drawn it without replacement, meaning I haven't put it back. And that means I'm only going to have 3 queens in my second event deck. And if I only have 3 queens, then the total number of cards has been reduced by 1. And so that means I'm going to have 51 cards, right? So 3 queens because I've assumed that I got a queen on the first event because I had to get a success on the first event. Otherwise, I wouldn't be calculating successes in total because I need to draw 2 queens, 1 on each event. And I don't get to replace it. So it means I've lost a queen. So now what we're multiplying is 4 out of 52 times 3 out of 51. So even though we did it by hand on the other example, we're going to go ahead and use a calculator here because those numbers are awful big and not easily reducible. So the first thing that we're going to do is we're going to reduce our fractions. So we're going to use a calculator to divide 4 into 52. 4 into 52 is 0.077. So that's our probability. So in other words, it's 7.7% that we will draw a queen from a standard deck times, and I'm going to go ahead and divide 3 into 51. And so that probability is 0.059. And so in other words, there's a 5.9% chance that I'm going to draw a queen when I've lost a queen, when I only have 3 queens and the deck is 1 card smaller. Now notice that these numbers are in fact rounded, so it's not going to get us an exact amount, but it'll get us close enough, it'll get us within the ballpark. Okay, good. And so now all we need to do, all that's left, is to multiply those together. So we have 0.077 times 0.059. And so that comes out to be a sum total of 0.0045. And so that's really, really small, right? That percentage is 0.45% likelihood that we're going to draw 2 queens in a row without replacement. So the last thing we want to do is compare this number, this decimal, to this number over here, to 1 out of 169. And so I'm just going to go ahead and reduce that fraction to a decimal. So 1 out of 169. And that number, also really small, but still bigger, because it is 0.0059, right? So it is bigger by 0.0014, right? So it's not substantially bigger, but it is bigger. It is importantly bigger, right? Because these numbers are tiny. And so the point of comparing these two is to say, not replacing that card, making those 2 dependent events, has a pretty serious effect. It makes this probability much less than the probability with replacement. With replacement really does improve your odds. All right, so that's the end of this example. Thank you very much.